Hi everyone, my name is Robert, and I'm a PhD student at Yale University, and I work in the Fabratory. And our lab studies soft robots. Now you might ask, what's a soft robot? Well, you might have heard of regular robots. Unlike these traditional robots, like the arm that you see on a manufacturing line, or maybe even in science fiction, the Terminator, soft robots are made from soft materials, not rigid, hard metal. So the advantages of soft robots are, one, they're really compliant and able to be dropped or sustain impacts without breaking. Second, they can be collapsed down to a really small footprint, and because of the materials they're made from, they won't break. Third, they can undergo a variety of really complex motions that traditional robots made from rigid metal can't. Imagine you as a human. Your arm isn't all rigid. You have rigid bones underneath, but you have muscles and ligaments that connect that together. And because of this, you can perform a variety of really complex motions. Similarly, a soft robot tries to do that. By using soft materials, we can get a variety of complex motions while remaining safe around people. So conventional robots use rigid motors, but we can't use those in a soft robot because they're not soft. Instead, we have to rely on different forms of actuating or imparting movement on a robot. A number of different methods are used, including chemical reactions, even using light or thermal energy. Here I have a pneumatic actuator. And what a pneumatic actuator is, it's just like a balloon with a directed motion. By inflating a pneumatic actuator with air, like I have in the syringe here, you can cause it to inflate, like this. And as you can tell, as I apply more air pressure into the system, it grows larger and extends further. So I introduced to you the concept of a pneumatic actuator, which we have here. And what we can do is use these as building blocks to create larger, more complex structures. So I have here a structure that consists of a variety of these pneumatic actuators across its faces. And what I can do is inflate these pneumatic actuators and cause the system to move. So for example, with this actuator on the front, when I inflate it with the syringe, you'll notice that it expands. If I do the same thing on the bottom of the structure where it's resting, I can cause it to flip over because it becomes unstable. We can extend this to make really larger soft robots, like the big brother of this one I have here. So you may be wondering, what are soft robots made from, and how are they made? Well, I'm here to tell you it's actually pretty simple. A lot of soft robots are just made from silicone rubber. This is material I have in the speaker here. You'll notice right now, it's pretty goopy. And I can touch it with my hands because it's human safe. By mixing two components together, we can create harder structures that provide the resistance to create actuators that you saw earlier. So we're over here at our polymer mixing station, and we're about to make our soft robot gripper. Now, how do we make it, you ask? Well, we use a mold. So first, let's mix the components of the silicone rubber together. Be careful to be exact with your ratios, or else the gripper might not turn out right. Now, let's mix part B. So, let's put it in the mixing machine. So, I'm simply going to pour it into this mold here. It's okay if you're a little messy. It's easy to clean up. So we've come back to our soft robot gripper that we just poured into the mold, and now it's totally cured. And it's a fully functional gripper. Let's take it out of the mold, and let's start grabbing things with it. So with this soft robot gripper, I can grab a number of different geometries, including this cup, this Rubik's Cube here, and even this skinny geometry, like this marker. The great thing about this soft robot gripper is that it's really easy to make, and it can conform to the shapes of different objects. So you don't have to have a specific robot gripper for a specific object. Instead, you can have this really simple, easy to make robot gripper for a variety of different objects. As humans, we're not really good at telling a robot to do a specific task. As you saw earlier, I can inflate the robot and cause it to tip over. But what if I wanted to do more complicated motion, like a rolling sequence? We have to rely on sensors to transfer data of a robot's position in space at a given point in time to a computer so that the computer can help us control the robot. Soft robots, because they're soft, can't use traditional sensors to figure out where they are in space at a given point in time. So we have to rely on soft sensors, which I have here. This is a stretchy sensor. And when I pull it, you can see the signal on the computer changes. The more I pull it, the larger the signal gets. And if I relax it, the signal goes back down. You'll notice as I pull faster, you can see multiple peaks. So with sensors like this, we can track the movement of a robot in space. And this allows us to feed that information into a computer to help us control the robot better. You may be wondering, how does a computer tell a robot what to do? And we can do this through a process called machine learning. If you imagine teaching your dog a trick, like to sit, what do? Well, you ask your dog to sit, and if they sit, you give them a reward, a treat. The same concept holds with computers and robots. When training a robot to do a specific task, if it does the task we want it to do, we give it a reward. If it doesn't do that task, we don't give it a reward. Over time, through a number of iterations, the robot learns to associate that reward with the behavior. So at the end of the day, the robot performs that behavior or motion really reliably. So I've showed you a lot of concepts today. We've seen actuators that make robots move. We've seen sensors that give us the ability to sense where a robot is in space at a certain point in time. And I also touched on machine learning, which helps us develop complicated movements for the robots relatively easily. So now, let's take all of these and merge them together in larger robot systems like the one I have here, this soft arm. This soft arm is like any other robot arm, except it's completely soft. And it can hold things and swing them around, like you see here. The advantage of this over a traditional robot arm are, one, it's way more flexible, and two, it's soft, so if it would run into you, it wouldn't hurt you. Now this example might seem a little silly to you, but the concept we have here is this soft robotic skin, as we call them, that integrates the concepts I've talked about, actuators, sensors, and computation. And these skins aren't necessarily made for a single platform. For example, underneath here, this robotic arm is just a pool noodle that we've wrapped the skins around. So as I disassemble this system, you'll be able to see it more clearly. We can take off one of the skins here and apply it to a totally different host body. In this case, this piece of foam here. So I'm just fastening it up here. So the idea here is in a relatively short period of time, with the same exact materials, sensors, actuators, computation, integrated into this very simple substrate, we can change from an arm to an inchworm type robot on demand. I wonder if you can imagine this little robot, what it could do in real life. Well, I can think of a couple of things. One of them being, what if there's a collapsed building and there's survivors under the rubble? A soft, squishy robot like this could squeeze into the rubble and look for survivors. In fact, you can even put sensors on this little guy to make him attracted to light. What great soft robot designs can you think of? Me, I imagine putting the robotic skins on a stuffed animal to give it the ability to walk, like this horse you see here. Pretty silly, isn't it? Otherwise, the design challenge is open. How do you think soft robots can help people in their day-to-day lives? What animals that we see in nature do you think could be great inspiration for soft robots? Who knows? Maybe you could be the next one to design a great soft robot.